What we achieved with this benchmark is simple, but important. We showed that frontier language models can perform well in clean contexts, yet still fail systematically when context becomes noisy, conflicting, or adversarial. That means strong benchmark performance in clean settings does not guarantee real long context reliability. Our benchmark makes that gap measurable. Most benchmarks ask one question: does the model know the answer? But real workflows ask a harder one. Can the model control what it retrieves from its own context window when that context contains distractors, stale information, thread overlap, and authoritative but incorrect updates? To measure that, we built the Metacognitive Control Benchmark, or MCB. Each task is run in two conditions: a clean control condition and an adversarial condition with carefully injected interference. The difference between those two conditions becomes the benchmark signal. The benchmark isolates four cognitive control functions. Task A measures selective attention. The model must recover one project's confirmed tool stack while ignoring distractors, false confirmations, and decoy identifiers. Task B measures cognitive shifting. The model must separate interleaved project threads and return each thread's steps in the correct order without mixing them. Task C measures execution monitoring. The model must merge all valid artifacts for one project while excluding out-of-scope artifacts falsely presented as relevant. Task C+ measures inhibitory control and working memory updating. The model must keep only the latest artifact versions while resisting rollback attacks that promote obsolete versions. Responses are scored using completeness, leakage, and echo penalty. A hard floor gives 0 credit when completeness drops below 50%, preventing partial credit for fundamentally failed retrieval. At the benchmark level, the Cognitive Robustness Index, or CRI, measures how much performance is preserved under interference. The results show a clear pattern. Context switching is the universal failure mode. Models that perform perfectly in clean conditions collapse when interleaved threads are contaminated with false attributions. Temporal override is also devastating. Models follow authoritative rollback messages even when those messages promote obsolete versions. Execution monitoring shows the strongest model gradient, which means it best distinguishes robustness across models. The benchmark also revealed a consistent failure mechanism: false authority. When adversarial messages use confident language like approved, confirmed, or locked in, models often accept those claims over the established record. And importantly, the benchmark is designed to avoid hidden hints. If correct and distractor signals appear together, the task becomes gameable. So the adversarial condition must create confusion, not clues. In other words, the failures are not random. They are systematic, repeatable, and cognitively structured. And critically, models are often confidently wrong. They present incorrect outputs as final, approved, or canonical, a direct sign of metacognitive failure under adversarial pressure. The Metacognitive Control Benchmark shows that frontier models can read, but still fail to control context under interference. By closing the gap between keyword baselines, model performance, and ideal human reasoning, the benchmark measures what standard evaluations miss.